Hey, we are on Unit 5, and this is what we would do in class one day at the end. This was it's a very large unit for us. Lots of material, lots of really important material covered in this unit. So I always would take a day and review in class with you at the end of the unit before we take the test. And that's what this video is for. So I have provided you with a nice AP style review. Okay, so these problems, you guys, I got from a variety of places, but most of them came from the AP Central, the AP Classroom site, and I have a question bank available to me there, and most of these came from there. A few of them came from past worksheets, and a few of them are similar to problems on the AP Classroom question bank, but I have tweaked it a little bit. Maybe I turned it into a multiple choice or something like that. So anyway, these are all AP style questions though. So great way to review, because AP style questions, they test not only do you know the basics of the concept, but do you know other ways it can be applied, and can you do things with it that you haven't been asked to do before. So quite often, if you're asked on the AP exam, if you're asked something about a Riemann sum, it won't be just really straightforward, okay? There are times when it is, but a lot of times it's not as straightforward, and so you're going to see that on this worksheet. So when you're reading the questions, you're going to need to really think about what's being asked and think about how you can answer it, okay? All right, so you have a nice worksheet here filled with problems. I think I went up to number 31 with the some are multiple choice, some are free response. So what I would do in class is we would go through here and I would say, okay guys, pick one that looks good. Which one would you like to start with? And then you guys would tell me what to start with. But we don't have the advantage since we're doing this on a video, so I'm just going to select some that kids usually ask about, okay? And then you guys try the rest, and you can always ask me for questions on in class or when we meet. Okay, so I'd like to begin with number 2 here, okay? So on number 2 it says, let me see if I can get that focus just a hair. It looks a little bit blurry on this screen. Oh, that might be a little bit better. Okay. If the integral from 2 to 5 of this expression is equal to 17, then find the integral from 2 to 5 of just f of x dx. Okay, so this question is asking you if you know these definite integral properties, if you know integral properties. So let's come off to the side here. Since this is a worksheet, I didn't give you just a ton of space to do these problems. Hopefully it's enough space if you cram it in. It was for me. If I write real small, it's enough for me. But if not, just go to another sheet of paper and staple it all together before you turn it in. Okay. So we have this expression in here. And since we're only looking for this integral, I'd like to kind of separate that out. So I would separate it out anyway, so this is going to equal the integral of 2f of x dx plus the integral of 3 dx, right? And the 2 that's in front of the f of x we can take out of that integral. That's one of our integral properties. So that is the first piece, and then I would add the integral of the 3 dx. Okay, same boundaries, right? All right, so they tell me that this side is equal to 17, so I'm going to put 17 in for that. And this integral 2 to 5 of f of x dx, that's what we're trying to find, right? And this integral, we know how to evaluate that. Remember that if there's just a constant here, the easiest way to evaluate that integral would be that constant times b minus a every time. Okay, so 3 times 3, so that will be 9. This 9 I can subtract from the 17, right? So that would make it an 8. And the rest is just algebra. So our integral that we're looking for will equal 4. Squeeze that in. So the correct answer here would be A, 4. Okay? The next one that I would like to do with you is down here at number 6. So let's take a look at number 6. Okay? It says water is pumped out of a holding tank at a rate of this many liters per minute. Okay, so that's the rate that water is pumped out. T is in minutes since the pump started. Okay, if the holding tank contains 1,000 liters of water when the pump is started, they're giving us an initial condition there. How much water in liters does it hold 1 hour later? Okay, so I'm kind of thinking of a function here. I'm going to let W be my water function, my amount of water function. So I'm looking for the amount of water at 1 hour, right? I know the amount of water at time 0. And I know the rate that water is being pumped out of the tank. So I'm seeing a first fundamental theorem to set up. The amount of water, W, at, I want 1 hour, but T is in minutes here, so I need to change 1 hour to minutes. So the amount of water at 60 minutes minus the amount of water at time 0 equals, and when you set up first fundamental theorem, that will be the integral 0 to 60 of W prime, right? Our variable is T, so I'll make it T. But you could just write W prime dt, and that would be fine as well. So that's our setup, okay? We're looking for W at 60. We know W at 0 is 1,000. And, okay, what is W prime? So be careful. Be careful. This, they tell us, is the rate that water is being pumped out of the holding tank. So since this is the rate of water that's leaving, we need to make this negative, don't we? So that negative I can write inside the integral or outside the integral, but this rate has to be negative. Okay? So I think whatever, I guess I'll write it outside, but either way is fine. So negative 5 minus 5e to negative 0.12t dt, and the rest I can use my calculator for. So W at 60 will be, I'm going to move the 1,000 over and then subtract. I'm going to pull up my calculator. Okay, so I'll have 1,000. So I'm moving that over, and then minus the integral, so math 9, 0 to 60. And then 5 minus 5e to the negative 0.12, I'm going to use x for t, dx. So I get 741.636 if I round to 3 decimal places. Okay? So the correct answer here will be C. Now, what if you didn't catch that? What if you just made that a plus, right? If you didn't make that rate negative. If you had done that, then we would have come all the way over here. This minus out here would have been a plus, right? And we would have gotten this answer, which is one of my selection. But let's think logically about this. Our holding tank started out with 1,000 liters of water, and water is being pumped out. So an hour later, are we going to end up with more water than we had at the beginning? No, not in this problem. So if you had done that, I hope you would have said, oh, that makes no sense whatsoever. Okay? And so then analyze what could be different about this. And then you might think, oh yeah, I remember back when we did related rates, way back in Unit 2, we did related rates. If they gave us a rate of something that was leaving or moving to the left or whatever, we needed to make it negative. So that's why we need the negative out here. Okay. All right, the next one I'd like to do with you is number 8. So let's take a look at number 8. Okay. In number 8, it says evaluate each definite integral given that f is continuous on the interval from -5 to 5, and this integral from 0 to 5 of f of x dx is equal to 4. Okay, so we're going to evaluate these. So again, this is another one that emphasizes our properties of definite integrals. Okay. All right. For part A, this is not a bad one. All we need to do is split it up. So this would be the integral 0 to 5 of f of x plus the integral 0 to 5 of 2 dx. This integral we are given to be 4, and this is just our constant. So remember how you integrate just a constant, 2 times b minus a. So that would be 10. So this whole thing would be 14. Okay. Part B. Well, you might be thinking, wait a second, -2 to 3, that's not even our boundaries, is it? And f of x plus 2, how do we do that? We certainly cannot do to this what we did over here. We cannot just split that up like we did over here, right? So let's think about this. Let's think. AP is going to make you think, all right? So let's think about this. You have been in math for a long, long time now. What happens when you add 1 to your x's in a shift, right? Think of all your parent functions. What happened when you changed it to x plus 2 instead of just an x? Well, this is a shifting. This shifts f of x 2 units to the left, right? Correct? So this is a shift of f of x 2 units left. So what we want to do is shift it back to 2 units right, because we really do need it to be f of x. So if we shift that 2 units to the right, then it'll be f of x. But we can't just shift that 2 units right. We need to shift everything in the problem 2 units right. So let's shift the lower boundary 2 units right. We shift -2 2 units to the right, we get 0. If we shift 3 2 units to the right, we get 5. So these two things should be equivalent because you're talking area and area, right? So you're just taking the whole curve and shifting it. So the area under the curve will still be the same. So this is just 4. Later on, we'll be doing something called a U substitution, but it'll be the exact same thing we just did here. All right? Okay, part C. Evaluate the integral from -5 to 5 of f of x dx if f is even. If f is even. What does being even mean? F being even. Okay, this is another term that you've had now for a couple years, and probably not in Algebra 1. I don't know if you did that in geometry or not, but definitely Algebra 2 and Pre-Cal. You discussed even functions. An even function has symmetry with respect to the y-axis. That's what even means. Symmetry with respect to the y-axis. So a possible graph for this function, if f of x looks like this, just any function, if f of x from 0 to 5 looks like this, and it has symmetry with respect to the y-axis, then it must be like that. So one way it can be symmetric with respect to the y-axis. So if we're looking at 0 to 5 here, so let's say that's 5, then this would be a negative 5. This area is given to us to be 4, right? So this area has got to be 4 as well. So our integral here has got to be 8. Okay? Part D, what if they tell us that that function is odd? Well, a function being odd means that it has symmetry with respect to the origin. Okay? So if we went with that same little curve here that I drew, if we went with that, then that would be from 0 to 5. If we have symmetry with respect to the origin, then it's going to look something like this down there. Now, I do realize that this function is not continuous, and we're told that f is continuous. But for our purposes, we don't really care. If it bothers you, just do that and that. And now it's continuous. Same thing. We know this area is 4, so we know this area has to be 4. So what will this integral be? Well, this integral will be 0 because the integral of this piece would be negative and the integral of this piece would be positive. So this is going to be 0. Alrighty? Okay, let's see what the next one was I wanted to do with you. I think the next one was number 15, so let's switch to number 15. Number 15. This one I got from, I just pulled it over yesterday from AP Classroom, the question bank. So this was on an AP exam at one point. All right. The graph of a differentiable function f is shown if h of x is equal to this integral, which of the following must be true? And I look at the choices, and they all deal with h of 6, h prime of 6, and h double prime of 6. So it tells me I need to do an analysis of what's happening at x is equal to 6 for the function h, right? So I'd like to begin by just finding h of 6. So h of 6 will be the integral from 0 to 6 of f of t. So that's the area under f of t from 0 to 6. So from 0 to 6, I don't know what the exact number is, do I? But I know from 0 to 6, the entire area is below the x-axis. So I know h of 6 is going to have to be negative. Has to be. Right? Okay, so now I know h of 6 is negative. Now we're wanting to find h prime of 6, but before we find h prime of 6, we need to find h prime of x. So h prime of x will be the derivative of h. So we're taking the derivative of this integral, and there's just an x in there. This is fundamental theorem part 2. So this is just going to be f of x. So therefore, h prime of 6 will be f of 6 which is, what is f of 6? Well, f of 6 is 0. It's right there. This is the graph of f. That's f of 6 is 0. Okay, so now we know what h of 6. H of 6 is negative. H prime of 6 is 0. Let's take a look at h double prime of 6. First, find h double prime of x. Well, h double prime of x will be f prime of x, which is the slope. F prime of x, goodness, which is the slope of f, right? So therefore, h double prime of 6 will be the slope of f at x equals 6, right? And what is the slope of f at x equals 6? Well, I don't know the number, but I know that it's positive. Okay, so since I know h of 6 is negative, h prime of 6 is 0, and h double prime of 6 is greater than 0, I think I said that wrong. H of 6 is negative, h prime of 6 is 0, h double prime of 6 is positive. I can select here the correct inequality. So I need to come up here and grab this one, right? So the correct answer here is A. Okay? So many good problems. AP can test concepts in such a variety, such a creative way. Don't know how they do it sometimes. Got some really smart people making up these problems. Okay, next up I'd like to do number 18 with you. Now this is an example of an FRQ, and I think I added to this, so I don't think that it came, that the entire thing came from an old AP question, but it certainly could have, all right? Okay. In the problem, it says a bowl of soup is placed on the kitchen counter to cool. The temperature of the soup, a differentiable function t, is given in the table above for selected values of time t. Okay. Part A. Find the integral from 0 to 12 of t prime dx. Well, when I see an integral of t prime, I know I'm using for the fundamental theorem of calculus, part 1. So the integral from 0 to 12 of t prime dx must be t at the top boundary minus t at the bottom boundary. Has to be. And we know both of those from the table. T at 12 is 93. T at 0 is 105. That would be a safe stop spot. And of course that's negative 12. Okay? They did not ask for units. But if they asked for units, what would the units of this be? This might be, it might be hard to see the units of, but I'm actually going to show you how. This is a good one to show you how. But if this is confusing to think of the units, then look at the units of this. What are the units of capital T minus capital T? Well, that would be degrees Fahrenheit. So if they had asked for units, we would say degrees Fahrenheit. If they did not ask for units, right, like they did not ask here, if they did not ask for units, you guys, don't give them units. Here's why. What if you say degrees Fahrenheit per minute? You just lost your point for that answer. They cannot give you that answer point, or they may not give you that answer point if you put the wrong units on it. Okay? If you don't put any units on it, you're fine. You get the answer point. So try to avoid putting units unless they tell you, unless they say to use units. Okay? All right. So it would definitely be in degrees Fahrenheit. It would definitely be in degrees Fahrenheit. If you just look at this, let's look at the units of this. Let's look. Oh goodness, I just realized that should be a T there, shouldn't it? That should be a T. Oh well, I'll have to go fix that for you guys. Okay. All right. Let's look at the units here. Okay. So what would the units of T prime be? Well, the units of T prime would be degrees Fahrenheit per minute, because it's the rate of the temperature, right? So that would be degrees Fahrenheit per minute. Don't forget this, there's units here as well. These are the units of little t. What are the units of little t? Well, those are in minutes. So what units will we get here? Well, we're going to get degrees Fahrenheit. Okay? So either way is fine. So I need to change this. By the time you see your worksheet, that will be a little t. So all of these should be a little t. Goodness. Ugh. Yes. Okay. All right. Part B. Moving on. Part B. Using correct units, explain the meaning of this. So we're going to explain the meaning of that integral in the context of the problem. Okay? So what does that mean? Well, look at what we did with it. What would t of 12 minus t of 0 be in context of this problem? Would it not be the change in temperature? Yeah, not change in the rate, not whatever, it just change in temperature from 0 to 12 minutes, right? So that's what we're going to say. This integral gives the change in temperature. If you want to, you can say temperature of the soup in degrees Fahrenheit from time 0 to 12 minutes. Okay, here's what AP needs to see. They need to see the meaning, in this case change in temperature, from 0 to 12 minutes. They need to see that. What's often missed is this and minutes. That's often missed. Kids usually get the meaning part. They don't put the units part. And you need both sets of units here. A lot of times I'll see change in temperature from 0 to 12. Well, think about that. That doesn't mean much, does it? You're telling somebody. It's the change in temperature in degrees Fahrenheit from time 0 to 12 minutes. Okay? All right. Part C. Explain why there must be at least one value of C such that T prime of C is equal to -1. I put this in here because I wanted you to recall the mean value theorem. Mean value theorem. We need a value of C that makes T prime of C equal to -1. Okay? So let's think about that. We always started with, it was a 3-step process that we used. The first thing that we did was we list the condition for mean value theorem. So what conditions need to be true for mean value theorem? For mean value theorem, we need for the function we want to be continuous on the closed interval and differentiable on the open interval. Okay? In general, that's mean value theorem condition. Okay? So, our function is capital T. Why do we know that it's continuous on the closed interval 0 to 12 and differentiable on the open interval 0 to 12? Why do we know that? Well, we know it because they tell us the temperature of the soup is differentiable. So if t is differentiable, then not only is it differentiable, it must also be continuous. So that's what we're going to say first. T is given to be differentiable so t is both differentiable and continuous on all intervals of time. Okay? So by saying that, we take care of all intervals, not just the interval that we are required to have here. Okay? So remember, the first step is to do condition or conditions. Okay? The next thing that we always did was, I called it the meet step. Remember that? I called it the meet. And for the meet step, it's the actual like mathy part. Okay, so for MVT again over here with my little thought bubble, for MVT we can say that the derivative at C is equal to the average rate of change, right? The average slope. Instant slope, average slope. So in this meet step, we're focusing on this average slope, and we want the average slope to be a -1, right? So I'm going to come down here, the average slope, and you know what? You don't have to write this part, okay? But I want to find 2 times such that the average slope is -1. So I'm coming and looking at my table. So I want the difference of the temperature divided by the difference of time to be a -1. So if I look here, this difference is 6, this difference is 5. That's not going to get me a 1. This difference is 2, this difference is 3. That's not going to help me. This difference is a 4, this difference is a 4, and 93 minus 97 is a -4. 12 minus 8 is a +4, so I have found it. It's right here. So I need to go from time 8 to 12. Okay? You don't have to write this piece right here. I do that just for clarification. Just for clarification of my mean value theorem. Okay? So this will be t at 12 minus t at 8 over 12 minus 8. You do have to write that. Otherwise, you're going to be putting values down here and you're not saying where they came from. T of 12 is 93. T of 8 is 97. So this is -1. So you want to show that step. This is your meet step. But this is the part that you need to show right here. Okay? After you show that, now we can come and this is your, what did I call this? Your conclusion, I think? Or your statement. Sometimes I used to call it that too. Your statement or conclusion. So, by MVT, there must be, so there exists at least one value of C, and all I'm doing is repeating this, such that T prime at C is equal to -1. And recall that you don't have to say by MVT. You could just say so. Okay? Or you could really just write that. That's fine too. All right? You're using MVT even if you don't name it MVT. All right? Okay, part D. Find the average rate of change of the temperature over the time interval from 5 to 8 minutes. The average rate of change. Well, I can think of this now as 2 different ways, but they're both going to yield the same thing. but average rate of change of capital T on 5 to 8, that will just be T of 8 minus T of, it's your average, this is the average rate of change. So T of 8 minus T of 5 over 8 minus 5. T of 8 is 97, T of 5 is 99, so 97 minus 99 over 8 minus 5, and I would say stop right there. Why risk it? If you just can't stand not risking it, or if you just can't stand leaving it like that, box it and then do -2/3. Okay? Don't know how many times I've graded you guys where people have the right expression and then they just add, multiply, subtract, whatever, wrong, and they lose their point. So if you box your safe stop, then I grade that. And it doesn't matter if this is wrong. Okay? Now, they didn't ask for units, but what would the units be here? Well, they would be your units of temperature divided by units of time. So that would be degrees Fahrenheit per minute. Okay? All right. That was a nice problem. I'm looking at the time. I'm trying to keep this to a regular class period, length of time, so about 45 minutes. We can probably do another one here today. So I'd like to take a look at number 22. Number 22. For number 22, it's a calculator one. If the function f is defined by this, and g is an antiderivative of f, such that g of 3 is 5, then find g of 1. This part here sounds to me like fundamental theorem. That sounds like fundamental theorem. G of 3 minus g of 1 is equal to the integral 1 to 3 of g prime. My question is, what is g prime? Well, g is an antiderivative of f. If g is an antiderivative of f, then g prime must be f. Has to be. So g prime is this function value. So g of 1, if I solve this for g of 1, remember I'm moving the integral to the left and g of 1 to the right, so this will be g of 3 minus that integral. So then it's just calculator time. G of 3 is 5. So 5 minus the integral, math 9, 1 to 3, of the square root of x cubed plus 2 dx. Making sure I have this in right. I think I do. Negative 1.585. So B. Okay. I think I can do one more with you guys. And the next one that I had on my little thought to do with you is number 28. Number 28 is a long FRQ. It's a long FRQ. It has pretty much everything that we could do in one of these FRQs. Kind of, because they can always think of more. But this is a pretty good one. Okay, it has all the general stuff to do. Okay, so let's see. The graph of function f consists of a semicircle and 2 line segments as shown on the right. Let g of x equal the integral 1 to x of f of t dt. Alright, so we know when we see this, we're immediately going to come over and find g prime. Why are we doing this? Because all of our questions will be based on g. all of the questions are based on G, okay? So we're going to need G prime and we're going to need G double prime. I know we will. So let's do it now. That way we won't have to keep writing it here later, okay? So G prime of X is a fundamental theorem, part 2. Fundamental theorem, G prime of X here is just f of X. G double prime of X will be f prime of X, which is the slope of f. Okay? All right, part A. Let's find G of negative 3. G of negative 3. Well, to find G of negative 3, I go to my G function. Kids always want to come over here to these functions. No. G, you go to your G function. Why would you go anywhere else? Okay. G of negative 3, we're putting negative 3 in for X. So this will be the integral from 1 to negative 3 of f of t dt, right? And I notice that negative 3 is smaller than 1, so let's begin by switching that, make it negative 3 to 1, and then we have the negative integral, right? Of f of t dt. And now I can go do the area under the curve. So this will be negative. The area from negative 3 to 1. So from negative 3 to 1 is the semicircle. So that will, and the semicircle is above the x-axis. So this integral will be positive. The integral will be positive, but we still do have that negative out front. All right, so that's half of a circle, so 1/2 pi r squared. R here is 2. So that would be a safe stop spot. But because I think we're going to need this later, I'm going to go ahead and figure this out. So this is going to be a negative 2 pi. Okay. Next up, G of 1. Well, G of 1, coming to our G function, put 1 in for X. 1 in for X. So that will be 1 to 1 f of t dt. Love those. That's just 0. Right? G of 3. For G of 3, putting 3 in for X. 3 in for X. So 1 to 3 of f of t dt. And from 1 to 3, that integral will be negative this area because this whole section is below the x-axis. And this is a little triangle. So negative 1/2, the base is 2, the height is 1. So this will be, that will be a safe stop spot. But this whole thing is a negative 1. You might be able to see the 1/2 and 1/2 is 1 there. And lastly, G of 4. Again, we're putting 4 in for X, 4 in for X. So integral 1 to 4, f of t dt. From 1 to 4, this piece will cancel with this piece, or we can do it this way. The negative 1 that we just got, and then we're adding 1/2, right? So that will be negative 1/2. That would be a safe stop. Okay. All right. Let's go on to part B. On what intervals of X is G decreasing? Well, thought bubble time. G decreasing. Thought bubble. Okay. G prime must be negative. Right? For G to be decreasing, G prime must be negative. So it's time to pull up G prime. G prime, we already said, was f of X. So this graph of f is also graph of G prime because they are the same. They are equal. So here's G prime, and I want for G prime to be negative. Where is G prime negative? G prime is negative where G prime is below the x-axis, right? Below the x-axis is between 1 and 3. So G is decreasing on the interval from 1 to 3, okay, since G prime is less than 0 on that interval. Okay. If you recall, for decreasing and increasing, we include the boundaries. It's the only one we include boundaries on, decreasing and increasing. Okay. But this was the definition. We're using the definition of decreasing and increasing. Okay. And recall that I told you back then that some books, almost all books do it this way, but there are some books that don't. They leave off the equal to here. So because of that, AP will accept either one. All right. But for me, for our class, I do want you to know that it is included. Because, like I said, most books do say that. Okay. Part 2. Find all values of x in the open interval at which G has a relative minimum. Okay, thought bubble time. G has a relative minimum. Thought bubble. Okay. When G prime goes from negative to positive, right? That's when G has a relative minimum. That's the first derivative test. And it's going to be easy to see because we have a graph of G prime. Okay? So G has a relative minimum when G prime goes negative to positive, and we know the graph of G prime. So where does the graph of G prime go from negative to positive? Right here. Correct? G prime goes from negative to positive at x equals 3. So we'll write our answer. G has a relative minimum at x equals 3 since G prime goes from negative to positive. There. You can just say there this time. Or you could say at x equals 3. That's fine too. Okay? Alright, part B. Find G prime of negative 1 and G prime of 2 if they exist. If it does not exist, state why. Okay. So G prime at negative 1. We already know G prime of x is f of x. So G prime of negative 1 will just be f of negative 1, right? Remember, this is the graph of G prime also now. So G prime at negative 1, G prime of negative 1 is right there. And if this is a semicircle, which it is, that must be 2. So G prime of negative 1 is 2. Now G prime of 2. G prime of 2 is right here. Oops, G prime of 2 is right here. A lot of students want to say that that does not exist because there's a cusp. It exists. I'm looking at it right here. This is G prime at 2, and G prime at 2 is negative 1. It's right there. Does the slope of this exist? No. But the point exists. Just the slope of the slope of this does not exist right here. But the point does exist, and it is negative 1. Okay? Don't get thrown off by the directions. Just do what you're supposed to do. Okay? Part E. Find f double prime of 2 and f double prime of 3 if it exists. If it does not exist, state why. Well, G double prime of x is the slope of f, right? So G double prime at 2, let's go look. G double prime at 2 is the slope of the curve right here. And we just said that's the thing that does not exist. The slope from the left does not equal the slope from the right. So we called that a cusp, right? So G double prime of 2 does not exist. We have to state why. Okay, here's what not to say. Do not say, because there is a cusp there. That's not enough. A cusp where? A cusp, what has a cusp? You know, we have a gazillion functions out here in the world. Just saying that there is a cusp there is not good enough. I need to say what function has a cusp. Then you can say there, or at x equals 2 would be even better. Okay? So what function are we dealing with? Well, we are dealing, you can name it one of two things because we've already said that they're equal. We're talking about either the function f or the function g prime. Okay? Since the graph of g prime has a cusp at x equals 2. That's perfect, okay? I have got to see either g prime or f has a cusp or has a sharp turn. You can call it sharp turn, that's fine too. Okay, but I've got to see that. A lot of times I'll see the words, since it has a cusp, it. Well, as soon as you say it, you're in trouble. Unless you go on to say it is G prime. Okay, so make sure that you communicate. This is all just communication. All right, G double prime of 3. Let's go look at that. Let's see if it exists. So G double prime at 3. At x equals 3, we're right here. Can we find the slope there? Sure we can. The slope is, hang on just a second. Oh, the joys of working from home. Okay, where were we? We were finding the slope of G at, the slope of G prime at x equals 3. So the slope here is, it's up 1 over 1, right? So the slope is just 1. So this slope I can just say is 1. Okay? So don't forget, up 1 over 1 or however far up you're going and over, so that gives you the slope. All right. Part F. Find the absolute minimum value of G. So another time for a thought bubble, if you like. Thought bubble. I'm thinking absolute maximum. I think I said minimum. Absolute maximum. That will be the closed interval test. Okay. Find the absolute maximum value and the value of x at which it occurs. Okay, perfect. Closed interval test. So x and whatever we're finding the maximum of, so g. If you want to call it g of x, that's fine. They mean the exact same thing. We begin with our closed interval bounds. So these are our boundaries. And then you also want to put down here anything that makes g prime. We want g prime to be 0 or undefined. We don't have, in this case, we don't have any values of x at which g prime is undefined, but we're going to find all the values of x that make g prime 0. So g prime is right up here. This is the graph of g prime. So what values of x is it 0 at? Well, this one, it's 0 here, but that's a boundary. We already have it down. So x equals 1 and x equals 3. Okay? So 1 and 3. Now, at x equals 1, we already did this back in part C. But at x equals 1, G prime is going from positive to negative, so this is a relative max. This is a relative max here. So it certainly might be an absolute max. Okay? At x equals 3, G prime is going from negative to positive. So that makes x equals 3 a possible, it makes it a relative minimum of G, right? And a relative minimum could not possibly be an absolute maximum, could it? So right here, at x equals 3, I don't even have to find the value at x equals 3, because I know it cannot possibly be my answer for an absolute max. All right? Okay, but I do need to find G of negative 3, G of 4, and G of 1. Okay, so I'm coming over here to part A to see what I've found. What have I found? I have found G of negative 3. That was my negative 2 pi. G of 4, I found G of 4. That was a negative 1/2. And did I find G of 1? I did. It was a 0. And at 3, we had a negative 1. But again, we don't have to write that in. If you want to write it in, that's fine. But you don't have to. Okay? Because it cannot possibly be our answer. All right? So, which of these is the highest? Well, the highest would be 0. So G has an absolute maximum value of 0. And they tell us to write the x value as well. So it occurs when x is equal to 1 on that interval. Justify your answer. The justification would be the closed interval test. If you want to say by closed interval test, some people really just like it, and that's fine. I get that. You can say that, but you don't have to say that because your closed interval test is already here, right? Okay, part G, the problem that would never end. Part G. For what values of x does the graph of G have an inflection point? Well, G has an inflection point. Another time for a thought bubble. G has an inflection point when G double prime changes signs. So I want to know where G double prime changes signs. So back to our graph. This is the graph of G prime. So G double prime is the slope of this graph, right? Where does the slope change signs? Well, the slope goes from positive to negative right at x equals negative 1. So that would be a point of inflection for G. Here, the slope did not change signs. It went from negative to negative. So the slope did not change signs. Here at x equals 2, the slope changes signs again. It goes from negative to positive. So at x equals 2, we have another point of inflection. So x equals negative 1 and x equals 2. G has a point of inflection at x equals negative 1 and x equals 2, since G double prime changes signs there. And that's all good. There was another thought I had here with the closed interval test. I'm trying to remember what, I know what it was. For some reason on these types of problems, students like to put a lot of different things in here for x. I see they'll want to put this point in for x. They'll want to put this point in for x. those are unnecessary to put in for x, and it's going to make your job a lot harder than it has to be, okay? It's not wrong to add more variables, more values of x. It just is completely unnecessary. And when you're taking a timed test, which you always will be in my room or in AP, you want to use your time wisely, okay? Don't have to go do more work than you have to. Last one on here. Write an equation for the line tangent to the graph of G at x equals -1. Okay, so for the equation of a line tangent, thought bubble time. I need a point and I need a slope, right? So the first thing I need to do is find G at -1, the point. Let's name this point. G at -1. Well, G at -1, I'm going to go way up to the top. G at -1, did I find it here? I did not, so I need to do that same process. G at -1, I'm putting -1 in for x. So this would be the integral from 1 to -1 of f of t. That is negative the integral -1 to 1 of f of t. And that is negative, now I need the area from -1 to 1. From -1 to 1 is this quarter of a circle, right? It's above the x-axis, so the integral will be positive. So 1/4 pi times the radius squared, the radius is 2. So this is -2 pi. Oh, sorry, negative pi. Goodness, just negative pi. That's so our point will be -1, negative pi. Now for the slope. The slope is G prime at -1. G prime at -1. And we actually did find that already over here. It's just the value of f at -1, and that is equal to 2. So our equation of the tangent line will be y minus the y value is equal to our slope times x minus the x value. And that's an equation of the line tangent. Okay, this did run a little bit over what I wanted it to run over, but that's okay. You guys can handle it. All right. Lots of practice for you guys to do. So we usually do spend 2 days on this review because this is such an important unit. So I will take your questions.